Hello everybody. We're going to get started in this video by I'm looking at page 43 here. This is the list of theorems that we talked about. And what I'd like to focus on are these two theorems, Theorem 2.4 and 2.5. Those are probably the most important two of the most important tools on that list. They have something to do with one-to-one and onto, helping us to figure out when a linear transformation is one-to-one or onto. Okay, so what I'd like to do is to just revisit a couple of examples that we already did. In example 5, see if we can use those theorems to decide whether those linear transformations are one-to-one or onto. Okay, so we're going to scroll back here. Okay, and find example 5, part A. So here was the linear transformation that we were looking at. Okay, and I'd like to pose the question, is that one-to-one and is it onto? So we'll sneak that into the bottom here. So question, is T one-to-one? And is T onto? Okay, well, if we start with the one-to-one part of that question, Theorem 2.4 is a very helpful tool for that. It tells us that a linear transformation is one-to-one exactly when the null space of the linear transformation is just the zero vector. Okay, so we can answer that question by looking at the basis that we found for the null space. Okay, here it is. And notice that the fact that the null space contains non-zero vectors, and it tells us that the null space is more than just the zero vector. So here's what we can say then to answer this question. I'm going to use blue here. Okay, so T is not one-to-one. Because of the fact that the null space of T is not equal to just the zero vector. It's our basis up here that tells us that. We can look at that set and notice there are two non-zero vectors in our basis. Okay. And what about onto? Well, here we might just make a couple of observations about how our transformation looked. Okay, so to be onto would mean that we need to be able to hit every vector in our codomain, R3. Now, how big is R3 as a vector space? What's its dimension? It has a dimension of 3. And then ask the question, how big is our range? Okay, well, our range, a basis for the range, just has 2 vectors in it. And 2 vectors is not enough. Okay, we can't make every vector in R3 just by taking linear combinations of 2 vectors. So here's what we can say. T is also not onto because of the fact that the rank of T is less than the dimension of R3. Okay, the rank again is just the size of the basis for the range. If there are only 2 vectors, okay, in 2 vectors in a basis for the range, that's not going to be enough, okay, to be able to hit everything in our codomain. All right. So we've answered the question then as to whether or not T is one-to-one and onto. Let's move on to part B, see if we can do the same thing here. Okay, so in part B, I'm just going to clear away a little bit of clutter here. Okay, this time our function looked like this, and we could ask the same question, is that one-to-one and is it onto? Okay, well, the one-to-one part of it, we can answer that question again by looking at the null space, and notice when we look at the basis for the null space, it's got a non-zero vector in it. So the null space is not just the zero vector. So again, we can conclude that T is not one-to-one. Okay, again, because of the fact that the null space of T contains more than just the zero vector. Okay, it's not equal to the zero vector. Okay, and just to remind you of the theorem number that we're using, that's Theorem 2.4 that says that. Okay, what about onto? Okay, well again, there we're asking the question, do we hit everything in our codomain? Okay, so there's our codomain R2, that has dimension 2. And notice that this time, the size of our range, basis for the range has 2 vectors, and so those two dimensions are the same. That tells us actually that T is on 2. Okay, because the rank of T, okay, again, that's just the number of vectors in this basis for the range, does equal the dimension of the codomain R2.